effects in semiconductors, known unknowns, and fundamental scales.
About something. Thank you very much. Thank you. So I had a question, what is Marburg? And who is Philip? Why we engage with Philip? It has nothing to do with Philip's enterprise. Philip's enterprise is with one P, or with two Ps. So this is Germany. And Marburg is 100 kilometers to the north from Frankfurt. And why were Philips? The Duke Philip founded us in the year 1527. So in a couple of years, we're going to celebrate 500th anniversary of the university. And that's how Marburg looked like that time. It has never been reconstructed. The state authorities never had money for that. It was a capital of state Hesse, and very soon after foundation of the state, the capital moved to the city where Bernd is living now, the previous speaker. And what we are doing there, everything related to disorder, but mostly transport, sometimes optics. And there's books, reviews, and so on, but exceptional today, I'm not going to talk about how clever we are. In this year, APS awarded the Oliver Buckley Prize for Outstanding Research in Condensed Matter to these three outstanding researchers. And it was awarded for pioneering research in the physics of disordered materials and hopping transport. And since I have listened many times about disorder, I decided I better present you the ideas of these great guys. Maybe they will be of some use for you, maybe not. And we start with a topic discussed in this workshop, semiconductor alloys. And I just present the idea of one of the recipients of the prize, Alex Efros. Don't pay attention to my name here. I was not yet a PhD student, so all ideas came from Efros. What is it about? You know, there's disorder, and it's not only nitrides. 2,6s also have disorder. And playing with the composition, for instance, in this material, you can manufacture the width of the band gap, in this case from 2.2 to 2.8 EV, which is favorable, but you pay the price, compositional disorder, which has been discussed many times here already. So for instance, you want composition X, and this is the dependence of the conduction band H on the composition, which I just borrowed from Claude's yesterday talk. And if you cut out some piece of the sample, you have fluctuations of the composition. I will be interested in fluctuations to the left in the band tail. So we cut some size R, and if there are much more than one atoms, we use Gaussian statistics. I have not heard your talk today. So it's just random distribution of A in B atoms. So the absolute variation is square root of the average number divided by the number of sides. This is a fluctuation of the position multiplied by this derivative. It's fluctuation of the potential. And you see, the smaller is the size of the fluctuation, the larger is potential fluctuation. It's natural. For the whole sample, there is no fluctuation. The smaller the size, the larger the fluctuation. The question is, what size to choose? And in fact, this question was addressed 10 years before we started by Zhora Salferov and his two colleagues, Efim Partnoy and Alexander Rogachev in YOFE. And their idea was just a heuristic idea. So what they say, OK, yes, we see the smaller the size, the largest potential fluctuation. But quantization level is pressed out of the narrow potential well. So on one hand, we want to have deep potential. On the other hand, we know we can profit from it. And the idea was, from all possible fluctuations, the most efficient are those who are narrow, but still contain potential quantization level. So these guys just equate these two energies, the depth of the well and the quantization energy. And this equation provides you some particular spatial scale. I will be talking only about scales, of course. Nothing possible else is possible. And inserting the scale into any of these two energies, we land up with some combination of material parameters. And this is assumed to be important energy scale in semiconductor alloys. And what we did was just checked this heuristic idea in the following way. So we're interested in some energy level below the band gap depth is given. Okay? This level can be produced by this classical fluctuation, or it can be produced by this very quantum mechanical fluctuation, where level is high, and by infinite number of other fluctuations. Okay? And we use the method of the optimal fluctuation. What does it mean? The potential energy is a function of the fluctuation. This is just the shape of the fluctuation. It can be any, not rectangular. And the eigenstate is, of course, also functional of the shape of the fluctuation. And then we put a condition that the eigenstate should be some fixed energy epsilon. And we just vary the probability of fluctuations, calculate the entropy. And found the most probable among all which have this given energy as an eigenstate. And this is the result. So this fluctuation appears most favorable to be responsible for this energy level. So the idea of Alférov and his colleagues is perfectly confirmed. It's very quantum mechanical. And already at this point, I would like to tell you why I couldn't sleep this night. Because yesterday we've learned that in this LL model, it's completely classical. And this very transparent ideas gives us high kinetic energy, completely quantum mechanical fluctuation. I have not found the answer. We should think about this. I'm not saying something is wrong, but there should be some merging of these ideas. It's too simple to be completely wrong. Okay, and then we know, because we know the entropy, we know the shape of the tail. So this is what Claude told us about yesterday. And due to this potential fluctuation, positional fluctuations, we have this bent tail. And Gaussian distribution of potentials provides completely not Gaussian shape of the band edge, because quantum mechanics was used in the bridge. So the message is, this is important energy scale, this combination of parameters. What is remarkable, look, this energy depends on the derivative as the force power of the derivative. This is the slope of the band edge with the composition. OK, this was about a single particle. Often people are interested in excitons. And then many people are tempted to say, OK, we have given size. This is a Bohr radius of the exciton. So just let's replace this R by the size of the exciton. And we have this particular expression for the energy scale. And you see it's proportional to the first power of the derivative. It's a completely different combination of parameters. And there are plenty of treatments using this idea, and it's continuing and continuing and continuing. And in fact, it's not very wrong if you are busy with impurity atoms. So if you have a donor, and it was known since 1975, many of us have not yet born this time. And it is correct for the impurity atoms. So if you have impurity atom in one component system, you have one energy for donors. If you have an alloy, because electron explores different compositions, we have spread of the donor functions. And now what Amorphous did, Amorphous said exciton is not an atom. Exciton can move. And what Amorphous did is the following. So we have potential acting on electron, we have potential acting on a hole. So we reformulate this problem in terms of relative motion and the motion of center of mass. We have shown an equation depending on both coordinates, center of mass and relative coordinate. And if we are in the Bohr approximation, so binding energy of the exciton is much larger than the typical scale of the fluctuations, we can factorize the wave function. And we obtain the Schrödinger equation for the wave function of the center of mass of the exciton, where potential terms are just convoluted with the internal motion of the exciton. In fact, that was the first idea of the effect of disorder on excitons. Beforehand, localized excitons were considered only in the way electron is bound on some particular center, hole rotates around, or vice versa. And what Amorphous said, no, fluctuations can affect excitons by center of mass motion and even localize the excitons. So it's just the proof that it was a pioneering idea. But I show this paper not just before of this reason. Claude wrote to us that we will have today evening some discussion. And one of the topics suggested was coherent potential approximation. And what Zimmerman and Schneider are doing in this paper, they're doing the following. They say, OK, we have potential acting on a particle. Who is the particle? Particle is the center of mass of the exciton. But the potential acting on this particle on the center of mass would be correlated in any case. Because even if you start with completely uncorrelated white noise, you will average this white noise by the size of the exciton. So the Bohr radius of exciton is announced as a minimum correlation length for the potential acting on excitons. And I would like to address particularly this detail. Let us look more carefully at the potential terms which act on the center of mass of the exciton. You see, just by exact formulation of the two-particle problem, we have potentials acting on holes and on electrons, not exactly the center of mass, but slightly shifted. This is, in fact, the reason why potential is averaged. But imagine that one participant of the exciton is much lighter than the other one. For instance, in 2,6 semiconductors, the hole is sometimes much heavier than electron. And then let us look, in this case, on the potential acting on the hole. You see, this term disappears in this limit. You take this potential out, and the rest is just normalization of the internal motion of the exciton. So potential acting on the exciton is bare potential, not at all smeared by the internal motion. Well, roughly speaking, the hole doesn't rotate around center of mass because hole is the center of mass. So the conclusion is potential acting on excitons is not necessarily correlated by the internal motion. And this is not restricted only to alloy disorder. It's for any disorder. It can be disorder of the width of the quantum wells and so on and so forth. But if you have, so it's on particles and on excitons. But if you have alloy disorder, this is solved as typical potential scales. But I repeat again, and this should be important for this audience, this is a result of the optimal filtration method, which is very transparent. Maybe it's wrong, but it's so easy that the discrepancy with your LL model should be figured out. So this night I had headache, but I had nothing to say to this topic, so I just changed the topic. And now I turn to another recipient of this Euler-Buckley Prize. And I changed the topic completely. Now it will be amorphous inorganic semiconductors. And it's just beautiful. First of all, these materials experience now a renaissance. I talked to Chris van der Walle, and he told me that he left the field. He was, in fact, one of the greatest guys in this field, but he said boring because nothing comes out. And now my message is it was too early, Chris. You know, for instance, amorphous selenium was material which made Xerox rich. This drum in the photocopying machine was done out of amorphous selenium. And now this material is actively used for medical imaging. And these are mammography detectors which you can buy, and they're industrially provided, and the same is with amorphous silicon. So I decided, well, you can learn more about applications, but I will focus myself on a beautiful scientific challenge, which was solved by Boris Kowalski, related to these materials. And we will restrict ourselves only to low temperatures, and it will be now about, not about transport, it will be about recombination. Well, it was just the first paper, then the field came out, and please don't think that I'm the boss of Kowalski and he's my student. It's just oppositely. All ideas came from student. He was Sherlock Holmes, and there were two Dr. Watsons, Helmut Frisch and myself. So now I would like to puzzle you, So, and the field was puzzled by about 10 years by absolutely contradictory experimental observations. But let's start from the beginning. So we have in crystalline semiconductors, we got perfect introduction yesterday from Claude, and I asked him a nasty question, because the question bothers me. What about amorphous semiconductors? Amorphous semiconductors also have bands. And Andrew Espenlaub is sitting here. Andrew, thank you. He said, OK, look, window glass is transparent. So there is a gap.
So, but where are the bands on this energy diagram?
Well, this is conduction band.
So where is it?
Delocalized states, above this level.
On this diagram, where is it?
Here.
Well, how do you make a difference?
How
do you make a difference between above and below the gap?
Because there is some level above which states are delocalized, so I put wave function here, do nothing, and it spreads over the sim. I put a function here, and I can wait as long as I like, nothing happens.
OK, so for you, the transition, the band edge is the transition between localized
exactly.
and delocalized.
Exactly.
This is the definition.
Exactly. It's called mobility edge because the spectrum is continuum.
Yes, but you don't see it on this diagram.
Yes.
No, it's physics. It's transport which tells you where it should be.
Exactly.
But this doesn't tell you where it is.
No.
Good.
Sure. No, of course, to decide localized or delocalized, I look here, not there.
So you have to do something more to know where it is.
OK. But again, let's start from the beginning. At the beginning is beautiful. Amorphous silicon gives you all recombination in radiative way. You know, crystalline silicon doesn't radiate at low temperatures. It's indirect semiconductor. You have momentum conservation rules, and so on. With amorphous semiconductors, somebody told it today already, and whether Stefan or the Bernd, that we lose momentum conservation if, or in the short talks, if we have disorder. That's the effect with.
So many people say.
Many people say it. I'm sorry. So it's completely radiative recombination, but it's a recombination between localized state. So we are now in the following model or situation. So the photon creates electron and hole. They relax temperature 0 into localized states, and they recombine from localized states. And because they recombine from localized states, this is a tunneling process. So electron has to go in space. And if wave function decays with some scale A, localization length will play important role in the rest of my talk. R is a distance, and this is just probability to find a particle at the remote place R, square of the wave function. And pre-exponential factor is just the spontaneous radiative falling down of electron in an atom. You create excited state, you look at your watch, several nanoseconds, electron is on the bottom. So we know the scale of this pre-exponential factor, and the localization length is also known for amorphous silicon. Now, if we study experimentally the decay of the luminescence after pulse excitation, we can figure out the distribution of the lifetimes. It's easy. And then we know the distribution of distances, and you see it is peaked at high temperatures at milliseconds scale. OK, we know it. For this part of my talk, two words will be very important. Geminate recombination and non-geminate recombination. You see, geminate recombination electron combines with the same hole with which it was created. And non-geminate electron from one electron hole pair recombines with the hole from another pair, created by another photon. Very simple. And now I show you experiments which clearly evidence geminate recombination. OK? Let me start. So this is a lifetime distribution as a function of the generation rate. So we pump more and more electron hole pairs into the system. And we see if we pump a lot of them, then the maximum starts to shift to shorter times because pairs start to overlap. The higher the concentration of pairs, the closer is hole from another pair to me electron, and the faster we recombine. But in the excitation range up to 10 to 20 photons per second per cubic centimeter, you see nothing happens. The maximum stays at milliseconds range, and it means pairs don't see each other. They live independently because I create higher density, but pairs recombine with the same time. So it's apparently geminate process. Oh, I'm sorry. Geminate process, at least in this range of excitations. If excitations are higher, pairs start to overlap, recombination becomes faster with higher density.
Are you pumping above or below the mobility edge?
Above mobility edge, but they fall down faster than they recombine. So they always recombine from localized states. But pumping is above mobility edge for sure. So it's geminate, OK? But if it's geminate, we would expect that under steady-state illumination, the steady-state concentration of electrons is just linearly proportional to the generation rate. OK? They don't see each other, so the higher we produce, the linearly more particles we will have. This is a result of the measurement under steady-state generation. And look, please, at the excitation range. It's below 10 to 20s. And it's extremely nonlinear dependence. So how it's measured is light-induced electron spin resonance. We know G factor. So we know steady-state concentration of electrons under given generation rate. And this is experimental result. And you see 5 orders of magnitude change of the generation, 1 order of magnitude change in the concentration. So it's not geminate. What to do? And it was for approximately 10 years a headache for the broad field, busy with inorganic amorphous semiconductors. So photoluminescence says it's geminate or proves. Steady-state concentration says not. And now I show you how Boris Kowalski, a recipient of the Oliver Buckley Prize 2019, resolved this problem. And the idea is, let us, for a while, be busy with the fate of just one electron hole pair. It will recombine geminately for sure, because it's just one pair. So hole will be nailed and don't move. You can relieve this condition, no problem. What happens with electron? Electron relaxes into localized states. And now there is an alternative, to recombine or to tunnel to another localized state in the tail. Electron can go only downwards, temperature is 0. We know already everything about recombination process. What is about tunneling? It is also related to the distance, exponentially. But pre-exponential factor here is completely different to the pre-exponential factor in the recombination process. Now, electron tunnels due to interaction with phonons. And here is something about phonon frequency. So there are 5 orders of magnitude difference in the pre-exponential factor. And what Boris desired, and it's, in my view, very beautiful, that there is scale constructed from these 2 pre-exponential factors and localization lengths. What is the meaning of this RC? It will be decisive spatial scale in the problem. If the distance between the electron and hole and the distance for hopping is smaller than RC, electron will tunnel, it will not recombine, because exponential factors are not important. So pre-exponential factors would prescribe to electron tunnel, although electron is situated in the same place in space, no tunneling. But electron will go apart from the hole because pre-exponential factors prescribe it.
But where does the 10 to the 13?
It's phonon frequency. The hopping transport, of course, it's tunneling due to interaction with phonons. That's it. Non-radiative, of course. So electron will not recombine, although it is in the same volume where the hole is. And then electron goes apart from the hole, and what happens when electron goes to the distance RC? Imagine this is trajectory of electron sitting here, and thinks, shall I recombine with the hole at the distance r, or shall I tunnel further on? Okay? And you know the decision comes from the comparison of times, and comparison of times is comparison of distances. And we forget for a while this distance RC because we are above RC. Okay? So we should decide what is longer, what is shorter. The distance to the hole, which is for Markovian case, is just determined by this expression, or the distance to the hole, or the distance to the next available nearest neighbor. And the tricky thing is, there is no preference. I just open all transparencies, not to make it secretly. So what happens? Electron is sitting, and after m steps, has some concentration of available sites. What will be with the concentration after electron makes a step? What happens with the concentration? In average, it will be halved. And the shape of the spectrum is not important. Density of states is not important. Electron goes down. So it can fall down to the closest energy, or it can fall down to the deepest energy. Who decides which energy state is the closest in space? Okay? Electron cares only about space. What energy comes is a random factor. So you multiplied the concentration with a random factor, and this is a new concentration available. Okay? So you see, in average, concentration decreases by a factor 2. It means, in average, the distance increases by a factor 2 to 1/3. Okay? And it means that the distance to the hole, this sum, is the sum of the geometric progression. And you know that the sum of the geometric progression by order of magnitude is equal to the last term or the next term. Just an example. You see geometrical progression. These are previous terms, this is next term. And it means that there's no a priori preference for electron to recombine or to tunnel. It's just what happens at this step is determined by the fluctuation in the distribution of sites below electron. Okay? It's just a feature of three-dimensional space. And imagine that there is some probability to escape at any step. Then what is the probability to survive not recombining to the distance r? If you need m steps for this escaping, so probability is q to the power m. Now we have to relate m with the distance, but we know every next step is by the same constant factor longer than the previous one. So we know how many steps we need to achieve distance r after RC. By these hand-waving arguments, it's this number, but in fact, it's critical exponent of three-dimensional space, nothing else. We are studying the feature of three-dimensional space, nothing more. And inserting this logarithmic dependence into this expression, we end up with power dependence on the distance for the probability to survive to this distance. It's just power function, and the power is a critical exponent in three-dimensional space. So this is prediction from the hand waving. Electrons do not recombine at short distances. Then, after the distance between electron hole arrives at RC, electron starts to recombine, so the probability to survive decreases. It's a probability to recombine, so it's probability density, mathematicians. To recombine is the derivative of the probability to survive. Okay? This is a project for the distribution of recombination distances from this hand waving. And now computer answers what happens in reality. So I just open all transparencies. So this is the result of computer simulation of this problem. Okay? And by chance, the maximum appears exactly at RC. So we know the time. We insert RC into the recombination time, and this is the expression. And you see, maximum in the lifetime distribution is constructed just from two parameters, from two pre-exponential factors. And if we believe in the phonon frequency of 10 to 13th and spontaneous radiative time 10 to minus 8, we end up with the maximum in the lifetime distribution. And this is a distribution of distances, which is a distribution of lifetimes for a single electron hole pair. So we are in the Geminate regime by definition. Now, let us calculate concentration of electron hole pairs under steady state generation is using this result. So what is the concentration? We multiply generation rate. G is the generation rate of all pairs, times probabilities to survive, generation rate of pairs with the length R. We multiplied it with the lifetime of these pairs, and we integrate over all distances, and this is the steady state concentration by definition. And what happens? This integral diverges, and it is apparent. Lifetime increases exponentially with the distance, but the probability to attain, to arrive at this distance, decreases, but just as weak power function. So we should care, in order to calculate steady state concentration, about the longest pairs in our system. And who are the longest pair in our system? It's obvious. The longest pair in our system are those in which electron left its geminate hole and comes closer to another hole. So the longest distance in our system is just inter-pair distance, roughly speaking, half of it. So we now calculate the steady state concentration under steady elimination. Left-hand side is the generation flux of these pairs with interside distance. This is the generation flux of all times the probability to survive to the inter-pair distance. And the right-hand side is the recombination flux of these pairs. So it's concentration divided by the lifetime. And lifetime is determined by tunneling over this distance. And we're interested in the dependence n on G, and we have n here, and here, and here, and G only here. And you guess immediately it's logarithmic dependence, because this n is more important than other n's. You can do it more carefully, and this is the result. And if you estimate, just take known parameters, there are just three parameters, two pre-exponential factors and localization length. And only out of these three parameters, we get the exponent as a logarithmic derivative in the dependence on the concentration on the generation rate. So what do we have? We have completely non-linear behavior. What does it mean? It means that this scale controls the whole recombination process. If the scale is smaller than the interside distance, what happens? Short pairs are created more frequently and recombine also more frequently. Some fraction of electron hole pairs created per second, small fraction with a power dependence, survives to the inter-pair distance. And those long pairs make the total concentration. So if you check only those who recombine, these are short pairs with the distance RC, with time scale milliseconds. But if you make a snapshot of your system and just look what are the distances on your picture, this will be distances, inter-pair distances. Okay? So this scale solves this long-standing puzzle. Luminescence geminate, steady state concentration, non-geminate. So small amount of pairs, they just go to non-geminate recombination and form the total concentration of particles in this system. Okay, so 2 recipients were here. Now the third one, Elihu Abrahams. He unfortunately passed away, but already after learned that he was awarded the Euler-Bakhtin Prize. And this is about hopping transport. And since there was some interest in hopping transport, Marcel told us you want to abandon mobility and go to hopping. Mobility is the main kinetic coefficient for hopping transport. So you should not abandon mobility. If Claude gives me 5 minutes this evening, I will try to focus on this topic. So what did Elihu Abrahams with his PhD student Alan Miller in the year 1960? They provided us with a method how to calculate hopping transport. First of all, they calculated the transition probability due to interaction with phonons between 2 localized states. So there is a spatial term because of tunneling, and there is an energy term if you have to interact with phonons and you need to borrow energy. But this is usually the only merit ascribed to Elihu Abrahams. And people usually oversee that in this paper, it's incredible paper by its efficiency, was suggested the recipe how to calculate the hopping transport. And the idea is you should deal with a resistant network, nothing else. So you just ascribe to each pair of sites in your system, to each pair of localized states, an effective resistance. So you calculate transition rate, its conductivity, inverse rate is resistance. Okay? And then what you should do, studying hopping transport, you should calculate the resistivity of this resistance network, nothing else. I can tell you this evening how. Now, or you just stop me and look into this book. It's everything. By the way, in this book you can find also all my words yesterday about percolation level in the classical potential, chapter 5, Psalm, Bible. It's called Bible in the book, really, in the community working with hopping transport. And now I will address just one feature because hopping transport is not my topic today. Therefore, it's the topic of Denis Andrienko. Therefore, I just address one feature, field-dependent mobility. You see, there is mobility for hopping transport, and if you're interested, I can tell you how to measure and how to calculate this mobility. And we will focus on the field-dependent mobility, and my goal is to end up with decisive, fundamental spatial scale responsible for this dependence. Before that, I will spend 10 minutes probably telling how to do it in the wrong way. And you can say, okay, why you tell us how to do it in the wrong way? Tell us the correct one, we are in a hurry. If I tell you the correct one now, first of all, you wouldn't believe. Secondly, you would forget it in a minute. But if I tell you what happens in the whole field, you probably will pay attention. If you open, there is at least 2 experts in this audience in the organic semiconductors. So if you open any edited book, monograph, review article, you find there this equation. So this equation for field-dependent mobility, this is field, this is mobility, this is KT. Who is sigma? Sigma is the width of the energy spectrum. There are good reasons to believe that energy spectrum, distribution of localized states, density of states, is Gaussian. So sigma is just the width of the Gaussian spectrum. So, for instance, in this recent 25th anniversary review article, there are just 2 equations. So what is this equation? In several review articles, I found the statement, this is most cited result in the whole context of transport in organic semiconductors. I cannot check, but probably it's true. It's more than 2,000 citations. Where it comes from? So in the 80s, last century, Hans Bessler with his colleagues did the following. They simulated hopping transport in a simple cubic lattice and fitted numerical data by this equation. In fact, they generally had some kind of special disorder. There were fluctuations of the overlap integral, but this equation with this number 225 is for the case without fluctuations. So just simple cubic lattice. 20 years later, the group from now real Philips with 1p did absolutely the same. They reduced the model of Bessel. They called it extended, but in fact, they reduced, they abandoned special disorder completely. So they simulated on the cubic lattice the same dependence and fitted the result with this equation. Okay? And this equation plays a very important role, not only for academic research. This is the basis for the commercially distributed software algorithms for simulation of organic devices, for organic LEDs. And what a coincidence. On the 17th of May, 2019, today, not far from here, in San Jose, they have a workshop where this software is presented. And software is based on this kind of equations. I cannot give my head that it is set forth exactly on this equation. Maybe it's on correlated disorder. But the previous version was on this. And the equation for correlated disorder has the same structure. So we're talking about the same topics. And now I take a liberty to present the cut from the review article of Denise Blom and others. And you see this equation is there. And this is only recently full description of field dependence and concentration dependence. And this is commercial advertisement for these equations. And now you see it's Phillips with 1p. And if this equation is so important, let us first check. Did it play any role that simulations were carried out on a simple cubic lattice? So what we did 2 years ago, first of all, we repeated their simulations. We did everything the same. And we, of course, obtained the same results for the simple cubic lattice. The same concentration, same localization lengths, same field, same disorder, everything the same. And equation describes it perfectly, you see. And then we did the only thing. We left all parameters the same. We just abandoned lattice structure. We just put the sites randomly in space. And you see what happens with the field-dependent mobility. You should be puzzled. All parameters are the same. Concentration is the same. So the conclusion is lattice model makes a lot. Mobility for spatially disordered systems is completely different to the mobility on the simple cubic lattice. Already interesting results, but not the main message. Imagine, I don't know, Richard might tell us, technologists, can they do polymers as a perfect cubic lattice? No. OK, thank you. But let's imagine they would be able. Now we would have a problem, because we now have two equations for the same feature. So which of these two equations would you choose? Imagine we have simple cubic lattice. Which of these equations should be taken? You should ask me, do they produce different results? Let's compare. And for comparison, we have just one parameter. Look, there is just one parameter in these equations, sigma scale of disorder over kt. So for comparison, we take the number 3. It's the mostly frequently idea for this parameter. And what a result. This is the field dependence of the mobility given by this equation. And this is the field dependence of the mobility given by this equation. We checked. Computers worked correctly. So these results are correct. For instance, I don't know, maybe squares are our results and circles theirs, or vice versa. And here we also confirmed the simulation results. So what was different? Different was one parameter. This is parameter about which I'm going to talk, or I'm talking now. This is localization length. There was only one difference in these two simulations. In parameters, simulations were identical. This group simulated for localization length. You remember, localization length is just a decay wave function. 1/5 of the lattice constant. And this group simulated this dependence for the localization length 1/10 of the lattice constant. And you see that this parameter, localization length, makes such a difference. Yes? And this parameter is not in the equation.
It's not in the equation.
No, parameter is not in the equation. That's my message. So equation is not at the level correct or wrong. It's senseless, because it doesn't contain the fundamental parameter responsible for the effect. And now, what is the correct description? First of all, there are a couple of students here. Students, never write such equations, because this is dimensionless. Here we have electric field under the square root. You know the dimension, square root of volt per meter. What experimentals usually do? They measure it. They plot logarithmical dependence of the mobility on the field and say, oh, we have determined parameter C for my material. Plenty of publications of this kind. But C is not a parameter. C is some interesting physical quantity with a dimensionality square root of meter per volt. Do you know? I don't. Students, how one should start? one should say the following. I want to put my field into its exponent. For that, I should make my field dimensionless. There is only one way to make electric field dimensionless. You build the product, charge field some length, and divide it by some energy. There is no other way. For energy, there are two candidates, KT and sigma, scale of disorder. What is the important length? This is my goal. What is the important length? You can see important length in this equation is a lattice constant. But in the year 1973, Boris Kowalski, the recipient of Oliver Buckley Prize 2019, treated this problem and claimed that the only important parameter is the localization length. It's completely counterintuitive. I agree. Completely counterintuitive. Electron gains energy tunneling over the intersite distance, in this case, lattice constant. So probably the normal researcher or normal human being would say, yes, this is the gain from the field. You will see this distance doesn't play any role. Everything is determined by this localization length. How Boris Kowalski came to this idea? It's usually very simple, by hand waving. So he said, OK, temperature is 0. My electron sitting here. I have some slope due to the applied field. My electron tunnels from this place to this place. It cannot climb an energy, temperature is 0. But nevertheless, due to the slope in the field direction, electron gains by this tunneling event this amount of energy. And the probability to tunnel is determined by this equation. And now I just replace x via this expression. So y acquired energy, and you see it looks as an effective excitation with some temperature. There is no real temperature. There is only temperature provided by electric field. And in which combination this temperature contains the field, in the combination as a product with localization length. So Boris say, OK, localization length is the only fundamental parameter. What do you believe? It's difficult. So what we did, we simulated, of course. We simulated not the lattice, we simulated a random system. And you see, this is random system, field-dependent mobility. Localization length is important. But we know whether it's the only parameter. So what to do? Just replot these dependencies. So far, we plotted as usual, keeping the concentration as a parameter. Now I put on this place localization length suggested by Boris Kowalski. What happens? So if you make a cross-section, localization length is fixed, but concentrations are 10 times different. But the field dependence is the same. So it is a clear proof that localization length is the only, so you shouldn't buy this equation. Localization length is the only fundamental parameter. And look what Shklovsky wrote in the year 1973. I have not yet started my study. And he wrote, you can use this dependence in order to estimate the characteristic length of the fall of the wave functions. He was so sure that his result is correct that he suggested to study this dependence to estimate the localization length. And which we have proven last year, yes, he was completely right. And there is another important statement here. So only recently, the dependence of the mobility on the carrier density was understood. If one treats the year 1960 as recently, it is true. You remember Elihu Abrahams suggested to replace our system as a system of resistances. And this is the real contribution of a couple of sites to hopping transport. There is distance, we know why. There is energy difference, we know why. But there is also the distance between the involved energies to the Fermi level. Why? Look at these two couple of sites, far above Fermi level. They're close in space and energy. But this pair doesn't contribute to hopping transport because there is no carrier. Both sides are far above Fermi level. Look at this pair. They're also close in space and energy. But there's no empty place to hop into. Both sides are occupied. So, and when we change concentration, we move Fermi level through the density of states. And of course, we change the mobility. And this is the reason why mobility is dependent on the concentration of electrons. Denise asked yesterday, Marcel, whether your mobility depends on the concentration of electrons. This is the reason for the question. In hopping transport, it does depend. In your case, it does not depend. You are absolutely fortunate. So you can even use this dependence to determine the density of states. We did it for a couple of years, and we have found out the density of states is Gaussian. just from the study of the concentration-dependent mobility. But for you, the message is localization length is the only fundamental parameter responsible for the field-dependent mobility. And now I very briefly address another question. In your LL model, of course, yes, thank you.
So when you compare the results, you're comparing the mobility fitted with this formula to the result from a percolation model with the Gaussian random disorder? Or?
You ask how we determine the density of states.
No. Previously, when you're comparing in this plot before, yeah.
Yes.
When you compute the mobility, you're comparing it to what? I mean, is this?
No.
To the for formulas or just?
No. This is numerical result.
Yeah, of course.
Yes. So we numerically calculate the dependence of mobility on the electric field, and now I have a good reason to explain how mobility is calculated in the hopping transport. Just to discuss with the poster where the bolded abandoned mobility go to hopping. So mobility is a good coefficient. First of all, you can measure it. So you just many ways to measure it. For instance, time of flight. So you take a sample, you create by short pulse carriers, you apply electric field, you have displacement current, you see it on the screen, okay? You know the transient time, you know the length of your sample. You divide the length by the time, this is drift velocity, you divide it by electric field, and you have mobility, okay? So it's how you measure it. There is different methods. How you calculate it, it's very easy. And now I have really a good reason to, thank you, to briefly tell you what to calculate and how. So there is some typical hopping length. Now it's intersite distance. So how to calculate diffusion coefficient? We should multiply it with some frequency. So what is wrong? Wrong is to average frequencies. Because if you average frequencies through the whole system, you average conductivities. It's the worst one can do to calculate the resistivity of the system to average conductivities. It is also wrong to average resistances through the whole system because there are many resistances which are extremely high, but they are not used by current. So what you should do, now to your question, you should use percolation arguments to figure out the real path which is used by electrons. And as soon as you have this path, you should average resistances along this path or hopping times. So you should divide this squared hopping distance by the average time, but averaged along the really used resistances. You can study it by percolation. I can tell this evening how. Or you can just fix the heat dissipation. So the places which provide the most heat are the most efficient. And now you should multiply it by, of course, generalized Einstein relation. Marcel, for you, Einstein relation is not generalized because you are in the Boltzmann limit. Your Fermi level is far below your transport path. So you are in the Boltzmann limit. It's normal E over KT. But in this hopping case, Fermi level is in the region where the hop, so the system is degenerate. So we should use indeed generalized relation. So I multiplied it by generalized Einstein relation, and this is the mobility. So I have mobility, I have diffusivity, I have everything. So it's not, if I calculate it analytically, I do this. But here it was just the drift divided by field, nothing more. And now we...
Where did you get from the percolation model with Basler?
Computer just takes a carrier. There is a field.
Yeah.
And computer moves this carrier.
Yeah, but you need a hopping rate.
Yes, computer knows all hopping rates. Yeah, but computer doesn't care about percolation. He just moves the carrier. That's it. OK, and now I also would like to very briefly address the last contribution, also because it came from Boris Kowalski. So Boris Kowalski was favored. There are 3 recipients. Elihu Abrahams gave us a recipe how to calculate hopping. Efros pioneered the effect of disorder on excitons. And Shklovsky did 2 things. First of all, he showed us fundamental scale for hopping transport. And secondly, Shklovsky addressed some problem which, in my view, also is related to the yesterday's Marcel's talk. You modulate your band edge by classical potential. Okay? And then you do the following. You start from each local value of the band edge, the square root density of states as if you have three-dimensional particles. I think it's true, because you have nanometers width of these wells. But in fact, one could check it in the following way. So these are just, it will not be about excitons. You have three quantum wells with a different geometrical widths. And these are just three spectral lines from these quantum wells. And the idea we addressed was what kind of fluctuations is more important. Because these quantum wells are built of alloys. It's 2 sixths, but these are alloys. So we have both. You have fluctuations inside the well because it's alloy, and you have, of course, your fluctuations of the geometry. And we were busy with the question which of these two mechanisms, disorder mechanism, is responsible for this broadening. And for that, you should try to answer the question: what happens with the density of states in the quantized system in the quantum well if you have disorder in the well? Okay? Do you have your quantization or not? As promised, I'm not talking about numbers, I'm talking about parameters. So in what language should you discuss this problem? And now I refer to Bernd Stock. You should compare mean free path with the geometrical width, of course. So you know, if mean free path is much larger than geometrical width, no scattering. When you establish coherent conditions, you have beautiful two-dimensional quantization staircase. If mean free path is much smaller than the width, geometrical width, you have three-dimensional case. So in fact, you should look whether you indeed have mean free path smaller than your nanometer size. I think you do. But just compare the numbers. It's no calculations. But for us, it's a challenge, because we know this extreme case, of course. But what to do if these two parameters, mean free path and the geometrical width of the well, are comparable with each other? Then one should think. And this is just the result. And the result is, here the density of states is plotted as a function of the ratio mean free path over the geometrical width. So this against square root, so the straight line is completely three-dimensional density of states. And this is two-dimensional picture. And what is interesting to look at is, of course, the derivative of the density of states, because the derivative in these points is just delta function. So the question is how this delta function is smeared out, how quantization is smeared out by alloy disorder inside the quantum well. And the answer is, you see that even if mean free path is twice as small as the geometrical width, you still have a kind of quantization. So this shows us how quantization conditions are affected by alloy disorder inside the well. The conclusion from the paper was it was not important. Important were geometrical fluctuations. Now my pointer is over, and it is a good sign to say that physics of disorder effects is fascinating. I hope you enjoy it, even if you do not use it. Yeah, for me it's just enjoyable, just aesthetic, nothing more. So doing theory, fundamental parameters should be figured out. And education is important, because if organic community had read the paper of Shklovsky that localization length is the only important parameter, they would probably try to parameterize their numerical results using this parameter. But they did not. So I was just lucky to be a PhD student of these two. And all ideas belong to them. Thank you very much for your kind attention.
Questions?
Maybe you can clarify something for me on the slide where you showed the rate of recombination versus the rate of hopping, and then you talked about these 5 orders of magnitude difference in the prefactor. So for the hopping rate, your prefactor is a phonon frequency.
Yes.
But in that expression for the rate, shouldn't there be like another prefactor? I mean, you emphasize the exponential, which has to do with the R dependence, right? But I think of hopping as going over a barrier, and that barrier shouldn't. I mean, I don't see where that barrier is in this.
The barrier, my pointer is out, so I use my finger. The barrier is in the localization length, of course. Localization length is the feature of your barrier. This is your barrier. This is
But is that
here.
barrier the same for recombination and for hopping?
Yes, because it is assumed, and there are good reasons, that the localized states in amorphous silicon just hydrogen-like wave functions, which decay exponentially, thank you very much, which some given localization length. So it's just your colleague Bob Street is the one who promoted this picture. Yes. So it is just a wave function decaying on some distance A, and he even determined that this distance is 10 nanometers. That's a barrier.
I honestly don't understand why the physics of the recombination process, Claude is nodding. I don't understand why that physics would have the same length scale as the physics of hopping.
Wait a second. So you have a localized state. Now it doesn't roll. Sorry? Look, your question is probably caused by multiphonon idea which you had in your talk.
I don't think so.
Here, look, this electron can do the following. It can recombine with the hole we're ready with it, right? What electron can do more? It can tunnel to the energetically closely lying in the tail another localized state. Both sides are hydrogen-like localized states. Localization length is the same, which is used by electron when it tunnels to this place to the hole. I don't see any problem with this.
As I was saying, for the hopping, I'm thinking of there being a barrier that you need to take into account, and I don't see that barrier playing any role in the recombination.
The barrier is here. Look, this is the barrier. If I go from here to here, this is the barrier, and this is localization.
Literally hand waving.
Sorry? No.
But I don't no, I mean, it doesn't have to be that as well.
I think it has to be.
Okay.
I think it has to be. It's the most sure part of this.
So in this rate, you always go downhill if it's allowed. So there is no barrier. If this state is lower than this one, you always go down. Where is the barrier?
The barrier is I go down under the barrier because this is conducting side. So this is the barrier between two sides. Even if I go down, there is a barrier to go down. Why this state is localized? Why wave function decays? Because it decays aside from my center under the barrier.
So usually you put temperature in as well for the hopping.
Yes.
And that would be the Mott Teeth-Corta law, which slows the hopping down.
It's another.
You can't hop very far if you just go downhill.
Yes. In the T1 quarter, just this parameter A comes straightly convoluted with the density of states. And Chris, I really don't understand. So all amorphous community is dealing within this set of ideas. Yes.
I have two comments to make. First, you asked me this morning for 10 minutes tonight.
I spent already.
Answered 7 minutes.
No, now of 1 minute.
Just you said 5 minutes, so that's
Yes,
great. So
yes.
everybody understands 5 minutes tonight.
Yes,
Okay,
not more.
Good. About the Baranovskii-Efros paper,
Oh, yes.
one comment, put it on your website, because in some places it's difficult to get. To get it here, I had to go to the inter-university system to get it. But we knew it in Polytechnic.
You are.
So if you have seen our paper
Yes.
on the simulation,
Yes.
there is a whole chapter, a whole paragraph
Yes.
on the comment from your paper,
I have no problems.
from which, of course you have no problem, but let me elaborate what
Thank you.
result we take from that.
Thank you.
From that paper where you give how to compute the localization from the location size from the fluctuation, the width of energy fluctuations. We compute a localization size for electrons of 2.8 nanometers in indium nitride and 0.1 nanometer for the holes. From there, we conclude that our Gaussian averaging distance which is 0.6 nanometer, is below what you predict as a localization. And therefore, we are correct to take this Gaussian averaging of composition to start to compute landscape, because indeed, we take something which is, we average on smaller sizes than what is predicted by your model.
You are talking now about LL model?
Yes.
Ah, so you relieve me from headache this night, right?
Yes, I think so.
You say you already were busy. Thank you.
To explain how we did it, and we use your results.
No, it's not about using my results. If there is some comfort between these approaches, because I was puzzled when Marcel tells it's classical, 86% potential energy. I knew already that I have only kinetic energy, but it's not a problem. Thank you, Claude. This is the best news I could have got here. Thank you. Thank you.
One word of comment about the, I think that the, what you showed here and the resistor network is exactly, I think, what we see in the landscape when we say, look at the overlap between the neighboring states.
Exactly.
See the
Exactly.
Exactly that.
Yes.
But and I'm not going to, I was not saying we have to abandon the concept of mobility. What I don't believe in is that mobility, an homogeneous mobility that you would put, because there are huge fluctuations. Even your localization length that you put here is a homogeneous parameter.
Of course.
It changes from side to side.
Of course, this mobility comes from macroscopic lengths.
And
sure.
If you are in 3D, 2D, or 1D, fluctuations of A can be drastic. So the reasoning that is here, that is, you know, the scaling arguments, I agree with that, and I think that the barrier, which is because the fluctuations of the alloy, they generate both the height of the barrier and the size of the localization length, and they're the same, both have the same origin. It's why your argument works. But I think I don't believe in the fact that you have an homogeneous A and that
not at all.
And that
it's simplification of course.
So yeah, and I think that the landscape is a perfect object to compute in a resistor network very fast.
Okay, Svetlana, I speak till 12 in fact. I refuse talking in the evening. I refuse talking in the evening because I just would like to react. Of course, calculating this resistor network, there are two problems. First problem, how to calculate. I don't know why why doesn't work. Both.
It works. Come on. You have to push the correct button.
No. I need to scroll it.
Ah.
Okay. So there are two different percolation problems. One percolation problem is yours. I'm still heard, or should I stop? Because what they did with is LL model. They have classical Himalaya mountain system. Okay? You want to go through Himalaya mountain system. What should you do? You should not assume that from the bottom everything is movable. It is delocalized in macroscopic sense. It's three-dimensional density of states. But there are walls, classical walls, so you cannot go out of the valley. Therefore, you should attain some percolation level. So you go higher, you have paraglider, okay? You cannot fly over the Mountain Everest. So you try to go as low as possible. But if you fly very low, you are locked in separate valleys. You go higher, now the valleys merge, and from some level, you can go through the system to the infinite distance from China to India, okay? So how to find this percolation level? It's very easy, and it's very classical. And you can ascribe the number mobility, and this mobility doesn't depend on the concentration of electrons. And this mobility is related to diffusivity by a standard Einstein relation. So how to calculate this level? First of all, it's via percolation. So you should solve percolation problem for your dimensionality. If it's two-dimensional, it's easy. Percolation fraction of conducting media should be 1/2. Because if you have percolation from east to west, you stop percolation from north to south. So it's exactly 1/2. In three-dimensional case, you should solve a really percolative problem. So you should paint the volume in this room. And if you do it randomly, in some color, green, okay? And you ask the question, what should be fraction of green color in this room to provide me pass to the infinity, the answer for uncorrelated painting is 17%. Because in three-dimensional case, you can just avoid difficult places. So you know 17% is the fraction of volume. You have in your LL model the distribution of potential. So you have distribution function of your potential, valleys and hills, okay? You integrate it over all potentials from minus infinity to yet unknown percolation level, and you equate it to the fraction of space you are painted, 70%. So you know statistical distribution of your potential, you know the percolation level, you know everything. You have conductivity, you have diffusivity. Your problem is very easy. Now, if you go to hopping, it becomes extremely tricky. Because first of all, you should solve percolation problem for your particular distribution of rates, okay? Then you know percolation threshold. And now you should average times, and it is not easy, because you have your percolation path, you should have it. And now you should average the times along this percolation threshold. So hopping conductivity is a tricky thing, and these guys did a great job. It's not Kubo formula. It's, if you make a photo of the system, all carriers are sitting. You don't see how they move. They move very fast, and then they're sitting. Claude disagrees with me. We can discuss it. But according to the commercial picture, and that's it.
I think there was a misunderstanding of the fact that it's the classical word that we use for explaining what the landscape potential is just to explain how we can, why the W mean, the minimum of the energy, gives a very accurate expression. It's because inside the main well, it looks like a classical object. It doesn't mean that it's not tunneling, and it's tunneling, and the resistor network that we have shown is the resistance on the resistor network. They come from the tunneling, and we have the estimate of the barrier.
That's true.
So we have so it's not a percolation problem in which we should be above the percolation threshold to tunnel. We are tunneling.
No. Tunneling above level, it's only for classically avoiding forbidden values.
This is not classical.
We are not classical.
It is classical.
He means confining.
You make quantum mechanics of that because you study the decay of the wave function and you calculate the transition probability. And my last remark, I will not speak this evening. Pay attention when you study these problems in disordered systems on the dimensionality of your system. Because sometimes people say, okay, for simplicity, we make the system one-dimensional. So imagine you make Himalaya mountain system one-dimensional. It's a problem now. It's a problem. And now, another very important feature comes in play. Electrons are not pedestrians. They don't climb to the mountain Everest. They tunnel underneath. How far? And there are two possibilities. Variable range hopping allows you to choose the way. So if the next energy is unfavorable, you just tunnel further on. And at lower temperatures, they do it. But if you force your electrons to hop only to nearest neighbor, it happens sometimes with people who treat hopping transport. So first of all, they take one-dimensional system, and they complete Himalaya in one dimension, and then they force to hop to only nearest neighbor. Why? Because there is machinery which calculates exactly hopping in one dimension nearest neighbor. So you should think what happens with your electrons, whether they go in the next valley or second next or further next. Thank you.
Sergei, what we are doing is somewhat different of what you are describing as an object. This was the comment also by Chris. In organics, indeed, you have well-defined molecules. This is not what we have.
Yes.
We know that we have localized states,
yes,
which are separated by barriers.
Yes.
And we can calculate completely the energy levels and the paths to relaxation, to transitions, to the Hagman distance. So we have no prefactors. We don't put 10 to the 13. We don't put 10 minus 8. We can compute everything. That's the difference with other computations of disorder, because we don't have adjustable parameters. And that's exactly what Marcel is computing.
You use Fermi's golden rule, right? So you have to.
Yes, but do you believe that, for instance, you have a linear relationship between the velocity and electric field? Because this is the definition of mobility. If it's not linear, it's not a mobility.
It's mobility field dependent. What is it?
Field dependent mobility is not a mobility then.
Okay.
The definition is a linear.
Okay. So Claude.
In classical meaning.
Claude, I got the message. I got the message. Thank you.
You see,
I got the message.
You were right, and I think we are right also.
I got the message. Thank you very much for your attention. I got the message. It's good that I'm here, because otherwise I would have been thinking about this.
And look at the